Hi, everyone. I'm going to be speaking about trade-offs for small depth Frege proofs. This is joint work with Tony Pitassi and Toniann. So this work is in the area of proof complexity, which is concerned with the following question. If we're given a universally true statement, i.e. a tautology phi, then what's the length of the shortest proof of phi? So if we wanted to prove or explain why phi is a tautology, how long does such a proof need to be? So mathematicians and logicians might be interested in this question just because it's a natural question in those areas, but computer scientists are interested in it because of what it says about the relationship between NP and co-NP. So Cook's program is based on the observation that NP is equal to co-NP if and only if there's a proof system such that every short tautology has a short proof. And we don't believe that NP is equal to co-NP exactly because we don't believe that this statement is true. As mathematicians and computer scientists, we have a lot of experience with short tautologies, short theorems that seem to have very long proofs. And so Cook's program, which is an approach to trying to prove that NP is not equal to co-NP, has the strategy that we're going to try and rule this statement out for increasingly stronger proof systems. So we'll consider a proof system, and we'll try to find a tautology that has to have very long proofs within this proof system. And as we rule out increasingly stronger proof systems, this should show us why NP must be not equal to co-NP. And so Cook and Rakow proposed in 1979 that we should consider the Frege proof system, which is a well-known proof system that is quite powerful. And trying to prove lower bounds against this proof system has remained a flagship open problem of proof complexity for several decades. So let me say a little bit about how this Frege proof system works. You can think of it as kind of like propositional logic 101 proofs. When you're just learning how to work with logic and how to manipulate logical terms, how you might prove statements. So if we want to prove a tautology phi, we start with the negation of phi, written as a CNF, and the goal is to use inference rules to try and derive a contradiction. So let's suppose that we have here all the different clauses of phi, of the negation of phi, sorry. And the goal is to try and show that it's impossible for all of these to be satisfied at once. So what we'll do is we'll grab several of them and we'll use inference rules to deduce new things that must be true if all of these statements have to be true. And so the goal would be to try and derive contradictory statements. So maybe we can, after several steps, show that if all of these clauses evaluate to true, then that means that X2 has to evaluate to true. But maybe in a different way, we show that if all of them have to be true, then not X2 has to be true. And because these are contradictory statements, that means that the CNF is unsatisfiable, which means that the original statement phi has to be a tautology. And within the Frege proof system, these intermediate steps of the proof are modeled by depth D circuits. So now how do we define what the length of a proof is? We define the size of the proof to be the sum of the sizes of the intermediate formulas of the proof. So these are the lines of the proof. And so we sum the sizes of all of these different circuits, and that gives us the size of the proof. And now there are a couple of different notions of depth that you might be interested in, but it turns out that the one that's most interesting is the maximum depth of all the lines. So we look at each of the circuits that are the individual lines of the proof, and we consider the maximum depth of all of these circuits. So now Cook and Rakow wanted us to try and prove super polynomial size lower bounds against unrestricted depth Frege. So that's showing that there are short statements that have to have long, i.e. super polynomial size proofs within the Frege proof system. Now, a standard fact tells us that it suffices to actually just consider logarithmic depth Frege proofs. And so the goalpost is set here at log of n depth. First, Haken was able to show in 1985 some super polynomial lower bounds against depth 1 Frege proofs, which correspond to the resolution proof system, which is an intensively studied and well understood proof system that's also the theoretical basis of practical SAT solvers. Later, these works by Aitai And Pitassi, Beam, and Pagliazzo, and Krajicek, Pudlak, and Woods were able to improve this depth 1 lower bound to log star of n and log of n. And these works sort of planted the seeds of the techniques that would be necessary in order to prove stronger lower bounds. So, but there's still this exponential gap between log of n and log of n. And this was partially closed much later by this work by Pitassi, Roseman, Cervedio, and Tan in 2016, which improved the bound to root log of n. And I want to note that we built heavily upon this work. And so I'll mention them several times in this talk. And then finally, about a year later, Hofstad was able to improve this result and get essentially quite close to log of n. So the size lower bound for depth d here is exponential in n to the omega 1 over d. And so this remains super polynomial as long as d is something like log n over log of n. But I want to point something that's kind of peculiar about all of these results, which is that there's supposed to be a statement about the size of the proofs, which, if you'll recall, is the sum of the sizes of the lines in the proof. However, if you look closely at these results, all of them actually just bound the number of distinct lines in the proof. And of course, if you bound the number of distinct lines, that bounds the sum of the sizes of the lines. But it's totally ambivalent about whether the lines are small or large. And naturally, if the lines are small, that's like a weaker proof. So we should be able to get better lower bounds. And so this is exactly the question that we wanted to answer. If we say restrict the sizes of the lines to be small, say polynomial n, can we get better lower bounds on the number of lines that must be in the proof? And so we're able to answer this question affirmatively. And so if we add the assumption that each line is a size S formula, then we show that the Frege proof must have size exponential in n over 2 to the roughly d root log s many lines. And it's maybe not so obvious to see how these two bounds compare, but for instance, if s is polynomial in n, so that this log s is basically like a log n, and d is like much smaller than root log n, so that this exponent is like much smaller than log n, then this bound is something like exponential in n to the 1 minus little o of 1, which is like strongly exponential. Whereas the above bound, because d is getting quite large, is exponential in n to the little o of 1. And so in this case, this does give a stronger lower bound. And so this identifies some new line size trade-offs for Frege proofs. But I want to point out that this isn't like a strict strengthening of this result, because if we increase d past root log n, then this doesn't really say anything, whereas this still remains super polynomial. And so this root log n point, it corresponds to the same point in the work of PRST. And so you can think of this as actually just a strict strengthening of that result. So I want to continue by talking about one of the key aspects of our proof, which is in its connection to circuit complexity. And so first I'm going to start by just talking at a very high level about the relationship between circuit complexity and proof complexity. And then I'm going to try and go into a little bit more detail about how the more technical aspects of these relationships work. So it turns out that these Frege lower bounds that I've been talking about in this long line of work correspond to AC0 circuit lower bounds. These results, these well-celebrated results in the 80s that showed that small depth circuits for the parity function have to be really, really large. And so these results were proved by switching lemmas, and the same switching lemmas can be applied to Frege lower bounds, but the difference is that we need to, whereas in the circuit lower bounds, we only needed to consider uniform random restrictions in our switching lemmas. For the proof complexity lower bounds, we need to consider non-uniform random restrictions. And now there's another kind of axis that we can have here where quite a bit later, these correlation bounds were proven for circuits, which are kind of, you can think of them as a more granular version of circuit lower bounds. So now they care about like, whereas these are kind of a binary thing, either a function computes parity or it doesn't compute parity. These are concerned with how close can a small circuit come to computing parity. I'll go into a little bit more detail about what I mean by that in a moment. And so Like I said, these bounds are proved via switching lemmas. And what you need to modify in order to get these correlation bounds is to prove multi-switching lemmas, where rather than just considering what happens when you hit one formula with a restriction, what happens when you hit many formulas all at once with a restriction. And so our work is kind of a blend of these two modifications. And so we are able to get these kind of more granular Frege lower bounds, these line size trade-offs, by proving a multi-switching lemma that applies for non-uniform random restrictions, the kind of restrictions that we care about in proof complexity. And so this is how we're able to get our lower bounds at a high level. So now let me go into a little bit more detail about the kind of upper part of this diagram I had earlier. So the punchline is essentially that proof complexity lower bounds lag behind circuit lower bounds. And so this is kind of the final result due to Hastad of this long line of work, that there's a linear size tautology such that every depth d up to log n over log n Frege proof of the tautology has to have super polynomial size. And all of these different works were basically improving what this bound here is. And this should be contrasted with the following parity lower bound, that every circuit for parity on n variables with the same depth must have super polynomial size. And so it turns out that these two results are deeply connected, but as you might imagine, it's not so obvious how to get from one to the other, as is evidenced by the 30-year gap between the end of this story and the end of this one. But by this point, the bounds are caught up, which is an amazing thing. The reason why they're so interconnected is because they share this common tool, which is the switching lemma. The switching lemma says that if we have a CNF and we hit it with a random restriction where we keep each variable with probability p as alive or set it with probability 1 minus p to either 0 or 1, then it's very likely to simplify significantly. In particular, it's likely to become a small depth decision tree. And so the idea is that, when you hit a function with a random restriction, like parity, it doesn't simplify that much, but the circuit computing parity simplifies significantly. And so it can, perhaps if it's too small, it's no longer going to be able to compute the complicated function. And so, like I said, the way that we get from circuit complexity to proof complexity is to adapt these switching lemmas to not just work with uniform random restrictions, where each variable is set independently from one another. Now we care about non-uniform random restrictions, where the variables might depend on each other or correlate with one another. So let me get into a little bit more detail about the parameters that we have here. So when we're considering the probability that a width W CNF is likely to become a depth T decision tree. And so Hastad's, in his switching lemma, was able to get a failure probability of PW to the T, essentially. I'm ignoring some constants here and throughout. So if we set P to be something like 1 over 10W, then this is going to be exponentially decaying failure probability as we increase the depth. And so these are kind of the ideal switching lemma parameters. And the kind of amazing thing about this result is that it has absolutely no dependence on n, the number of variables in your CNF, which is quite a surprising thing if you think about it. So now when we're switching to the proof complexity world, these results that I mentioned earlier were also able to prove a switching lemma, but they needed to have this factor of n in the base, which is in part why the bounds were quite different. But they had the benefit that the switching lemmas were able to apply to the non-uniform random restrictions that we needed to consider in proof complexity. Then this work by PRST was able to get rid of this n in the base at the cost of replacing the w with a 2 to the w, which initially sounds like it could be really bad, but it turns out not to affect the bounds too much. And so this work pioneered this random paths technique, which is this very simple and very elegant way of proving switching lemma bounds. And because of its simplicity, it's easier to show that it will work as well for non-uniform random restrictions. The only thing is that it has this cost of this 2 to the w in the base. Finally, this work by Hastad was able to improve these parameters by getting a t in the base and getting the 2 to the w back to a w. And it turns out that for this specific application, this t in the base doesn't end up causing any issues at all. And so that's why the bounds essentially end up matching up at the end of the day. And now that we're switching into these more granular results, like I said, the line size trade-offs that we prove correspond to correlation bounds. So what are these? So here's another statement of the parity lower bounds that I mentioned earlier. So every depth D circuit for parity on n variables has to have size at least exponential in n to the 1 over d minus 1. And so this says that small circuits can't compute parity exactly. But is it possible they could come close? Could a small circuit be could it agree with parity on 51% of the inputs, or maybe even 99% of the inputs? And so this line of work by Impagliazzo, Matthews, and Paturi and Hofstad were able to show that essentially the answer is no. So if you have a depth D circuit that's size S, then it agrees with parity on at most 1/2 plus this very tiny fraction of the inputs. And if you look at the parameters carefully, you'll see that essentially if the size of the circuit is just a little bit smaller than this parity lower bound, then it has basically no chance of doing better than 1/2, which you can get easily with just the all zeros or all ones function. And so these are kind of more granular results about in circuit lower bounds, because now they care about the size of this circuit and they ask a more granular question about how well they can compute parity. And so now the key tool here is the multi-switching lemma, where now we're considering a collection of CNFs rather than just one. And we care about the probability that they're represented as a single common tree with different smaller trees at its leaves. So what does this look like? So here we have a bunch of CNFs, and when we hit it with a random restriction, what we're hoping to get is the following thing, where each of these are decision trees. And at the top here, we've got the same tree, the same slightly bigger tree for all of the different restricted CNFs. But they're allowed to differ in these smaller trees that are at the bottom of the bigger tree. And so those can be unique to each of the CNFs. And it turns out this is exactly the kind of structure that one might want if you want to prove these more granular results like these correlation bounds. So now, once again, let me get into the parameters a little bit. So let's say we have S CNFs, and we care about the probability they'll become a depth T common tree with smaller depth L trees at its leaves. So these works that I mentioned earlier are able to get basically the same switching lemma parameters, but now with this S to the T over L on the outside. And you can think of this as like S choose T over L. And so now these are like the dream multi-switching lemma parameters that we would want to get. And so in this work, essentially, we're able to get the same thing, but now the W becomes a 2 to the W, kind of similar to how the PRST switching lemma parameters, how they compare to the Hofstad switching lemma parameters. And so here, once again, we use the random pass technique, which is again able to adapt to proof complexity, but it takes a little bit of additional effort because this is the first time that we're using a multi-switching lemma in proof complexity. And so it takes a little bit of effort to adapt that to the proof complexity setting as well. So now to go over how the bounds work. So here is the correlation bound that I mentioned earlier, the optimal one. And if you were to prove a correlation bound with our multi-switching lemma, these are the parameters you'd get. So you still have this kind of exponentially decreasing quantity, but the exponent is a little bit different. And it turns out that this exponent corresponds exactly to the line lower bound that we get at the end of the day. And so now, of course, the natural question is, can you actually get this as your line's lower bound? And so that's essentially the conjecture that we have, that you should be able to get that this is the correct number of lines that we should be able to prove as a lower bound. And so this would sync up with the optimal correlation bounds in the same way that the Frege proof size lower bounds now match with the circuit complexity parity lower bounds. One thing I will note is that if you were just to prove a multi-switching version of Hofstad's result by having this S to the T over L in front of the same parameters, you wouldn't actually get this because this T in the base actually ends up becoming a problem. So you might have to use newer techniques in order to prove this conjecture. And so with that, I'll conclude. Thank you very much. And I'm happy to take questions at the conference.